Hi, and welcome to our final day of new material for our semester of remote learning. Today we're going to be talking about section 14.2 and 14.3, and we're going to be talking about applications of partial derivatives. So last class I introduced the idea of what a function of more than one variable is, and I introduced the idea of what a partial derivative is and how to calculate a partial derivative. What I didn't talk about, and what I bet I left many of you thinking at the end, is what the heck is the purpose of these things? And so our goal today is going to be to take a look at two examples of using partial derivatives and interpreting what those partial derivatives can tell us about predicting things that may happen to cost functions or to profit functions or to revenue functions. Okay, so last class we talked about an example of a candy company that makes two kinds of candy, Kisses and Creams. And their profit is measured by the function p of xy is equal to 10x plus 6.4y plus 0.001x squared minus 0.025y squared, where the x variable is the number of pounds of kisses produced and sold, and the y variable is the number of pounds of creams produced and sold. Okay. And last class we calculated the value of p of 100, 16, and what that meant is that we plugged in 100 for x and 16 for y, and we came up with a value of 1,086, and that value represents the company's profit in dollars from the production and sale of 100 pounds of Kisses and 16 pounds of creams. And we also calculated the partial derivative of p with respect to x, and that's that funny looking dp over dx, and our partial derivative of p with respect to y, which is our dp over dy. And the values that the formulas that we came up with are dp over dx equals 10 minus 0.002x, and dp dy is 6.4 minus 0.05y. And so the idea was, when we calculate the partial derivative with respect to x, we think of x as the variable and y as a number. And when we calculate the partial derivative with respect to y, we think of y as the variable and x as the number. Okay, so what we want to talk about is we want to talk about interpreting partial derivatives. But before we start talking about interpreting partial derivatives, I want to remind you from earlier in the semester when we talked about marginal profit and we talked about marginal revenue and marginal cost, and we talked about how each of those describe for us the change in profit from the production and sale of the next unit of our product. Okay. So in particular, if we're talking about marginal profit, the p of x function is the total profit function from the production and sale of x units of a product, and p prime is our marginal profit. Now, when we talked about this in the context of functions of one variable, x is the number of units produced and sold, and when we take the derivative, that marginal profit, the derivative function, predicts the change in the profit. It says how much is the profit going to increase or decrease if we increase the number of units produced and sold by 1 unit. In other words, it's a predictor that gives us sort of a short-term prediction on what will happen to the profit if we increase production and sale by a little bit. Okay, so that was the idea that we talked about with a single variable, which is regular functions p of x. You might want to maybe pause the video and go back and check your notes on that section if you feel like you need a refresher on something like that. But now we want to talk about how to interpret these partial derivatives. keep in mind this idea of marginal profit, marginal revenue, and marginal cost with a function of one variable. Okay, so when we have a function of two variables, maybe p of xy, we call that the joint profit function. And so let's say we're talking about a joint profit function for a company that produces two products, A and B. Then we might say that the x variable is the number of units of product A produced and sold, and the y variable is the number of units of product B produced and sold. So in this case, our company is producing two products. Then p of xy, instead of called the total profit function, we call it the joint profit function for products A and B. And once we have a function of two variables, then we have two partial derivatives. The partial derivative of p with respect to x, and the partial derivative of p with respect to y. So dp over dx, the partial derivative of p with respect to x, we call that the marginal profit with respect to x. And what dp over dx tells us is, this says, okay, we are going to allow the product that's associated with x, so in this case product A, we're going to ask what happens if we increase production and sale of product A, but leave product B with its sales and productivity remaining constant. Okay, so the marginal profit with respect to x predicts the change in profit from the production and sale of the next unit of A, while product B's production and sale remains constant. Okay, so take a look at that sentence again. The marginal profit with respect to x predicts the change in profit from the production and sale of the next unit of product A, while product B's production level remains constant. So when we're talking about a partial derivative with respect to x, the math behind it says treat x as the variable and treat y as a constant or as a number. So the way that corresponds to how we interpret this in the context of producing and selling two items is that we're allowing that first item, the item associated to the variable x, we're allowing that item to be increased in terms of production and sale, and that second item, item B, which is associated to the y variable, that product is remaining constant. We are not going to produce and sell more or less of that product. That product is remaining at its current production level. All right, so that is our marginal profit with respect to x, or dp over dx. We also have our partial derivative of p with respect to y, and this is our marginal profit with respect to y. And this is going to be a similar description, except that the item that is going to be increased in terms of its production and sale is switched with the item that is going to have its production level remaining constant. So our partial derivative of p with respect to y says that we want to know what happens to the profit if we increase the production and sale of product B, but keep product A's production constant. Okay, so let's take a look at our example. In our example with the kisses and the creams, we had a partial derivative with respect to x, that's our marginal profit with respect to x, and our marginal profit with respect to y. And earlier in last class, we talked about the total profit from producing and selling 100 pounds of kisses and 16 pounds of creams. Now we're being asked to evaluate and interpret dp over dx of 100, 16 and dp over dy of 100, 16. In other words, marginal profit with respect to x evaluated when x equals 100 and y equals 16, and the marginal profit with respect to y when x equals 100 and y equals 16. Okay, so we'll start with the partial derivative with respect to x, And when we do that, everywhere that I see an X, I replace it with 100, and everywhere I see a Y, I replace it with 16. For our partial derivative with respect to X, there are no Y's in the formula, in this particular formula, and so we plug in 100 for X, and we get out a value of 9.8. Okay, so let's talk about a label for our partial derivative. So whenever I think about a label, I can look at that dp over dx. And what I want to think about is that our profit, the P on the top, is measured in dollars, and the X, the value in the bottom, is a measurement of pounds of kisses. So when I think about the label on the 9.8, that label is going to be dollars per pound, but because I have both kisses and creams, I need to distinguish between the two. So instead of just having dollars per pound, my label is going to be dollars per pound of kisses. So I want to make that explicit when I'm writing down my label. Dollars per pound of kisses. Okay. So now I want to think about what is the interpretation of this $9.8 per pound of kisses. Okay. Now when we talked about marginal profit in the past, that marginal profit says this will be the increase in profit for an additional unit produced and sold. But here I need to be a little bit more specific, because here we're increasing the units sold of kisses, but we're keeping the creams constant. Okay. So as of right now, the company is producing and selling 100 pounds of kisses and 16 pounds of creams, and we are increasing the kiss production, but not the cream production. So one way to write the interpretation is, for a current production level of 100 pounds of kisses and 16 pounds of creams, the total profit will increase by approximately $9.80 for a 1 pound production increase of kisses. And an additional important piece to note is that while we are increasing the production of kisses, we are keeping the production level of creams constant. Okay, so that is our partial derivative of P with respect to X, also known as marginal profit with respect to X. We're increasing the production of kisses, keeping the cream production constant, and by increasing the production of kisses, we are increasing our profits by $9.80 when we increase our production of kisses by 1 pound. Okay, so now we can take a look at our partial derivative of P with respect to Y. So we need a new screen here, and now we're going to evaluate dP over dy. Okay, so our partial derivative of P with respect to Y, evaluated at 100, 16, says that everywhere that I see an X, I replace that with 100. Everywhere I see a Y, I replace that with 16. Plug in the numbers, I get 5.6. And then when I put the label on the 5.6, my label, I can look at the name dP over dy, and the P on top is profit, so that's measured in dollars. The Y in the bottom, the Y represents the number of pounds of creams. So when I think about the label for dP over dy, that label will be dollars per pound of creams. So we end up with 5.6. Okay, so before you continue on with this video, I would encourage you to pause it and write down how you would interpret this value based on kind of the model that we used for the partial derivative with respect to X. So write that down, take a moment, and then compare it to what I'm about to write on the screen. No, really. Pause the video. Okay, so let's take a look at what that interpretation is going to be. So for a current production level of 100 pounds of kisses and 16 pounds of creams, the total profit will increase by approximately $5.60 for a 1 pound increase in creams, and by keeping production of kisses constant. Okay. So again, when we take our partial derivative with respect to y, we're asking what's happening to the profit if we increase the cream candy production and keep those kisses constant. Okay, so now we have both of these pieces of information. We have identified that if we increase the kiss production by 1 pound, then we are increasing our profits by $9.80, whereas if we increase the cream production, then we are only going to increase our profits by $5.60. So kisses will increase by $9.80 per pound, and creams will increase our profits by $5.60 per pound. And so it would make sense then if you as the person who's making the decision in this company, it seems like a good decision would be, hey, let's raise the production level on the kisses, because that small incremental increase, that 1 pound increase, is going to increase our profits more than the 1 pound increase of creams. So our conclusion is that the marginal profit for kisses is greater than the marginal profit for creams. And that tells us that an increase in kiss production will yield a greater increase in overall profit than an increase in the cream production.